To Professor Sir Nigel Shadbolt.
Well, that's a very nice workmanlike introduction. There's kind of no faffing about. So this is an audacious talk, really, because I'm going to try and give a little bit of a biography, my own kind of journey through AI via the topics. And really, it's almost 3 talks in one. But hey, we've got 45 to 50 minutes and half an hour to talk, apparently, in questions. So why not give it a go? I just want to first of all kind of acknowledge my thanks to the British Computer Society. I am a past president, in fact, in 2006, the 50th anniversary of the British Computer Society. And I remember one of the great joys of that year was going to Bletchley Park and being involved in switching on the bomb, which was not the first time it had actually been switched on, but it was a kind of a public unveiling. Alan Turing's A Masterpiece of Electromechanical Computation. And just again, you know, realizing how technology accelerates and what the ambition and audacity of that achievement was. And I guess my own journey through all of this has been very much about almost a childlike fascination with the big questions. So there's this wonderful quote that, of course, comes from Charles Darwin. There's a grandeur in this view of life, that a form so simple is beginning endless from so simple a beginning, endless forms, most beautiful and most wonderful, have been and are being evolved. And you can look at that at kind of cosmological level or in terms of our own brains. And the challenge, the inspiration always for me was consuming bucket loads of very cheap science fiction where the robots were already built, they're already self-aware, and the extraterrestrials were all out there. I thought it was just brilliant. I could never imagine I'd be able to work in the area, but of course the way I got into the field was through to imagining that we could use AI and computer models as serious gateways into understanding human intelligence. And in fact, my first degree was in philosophy and psychology, and I was just reflecting tonight with an old colleague just how that combination of psychology and computing, AI and cognitive science has been around as an inspiration for a long time, and it waxes and wanes in various ways, and we'll see some of that in the ideas that I'll present tonight. The other thing that absolutely blew me away, and I always imagine everybody knows and seen the track, you know, the wonderful Mad, Bad and Dangerous to Know How the Computer. And you remember this.
No 9,000 computer has ever made a mistake or distorted information.
Not yet, it hasn't.
I am constantly occupied. I am putting myself to the fullest possible use, which is all I think that any conscious entity can ever hope to do.
There's a thought.
I'm sorry, Frank, I think you missed it. Queen to bishop, free. Bishop takes queen. Knight takes bishop, knight. Thank you for a very enjoyable day.
Open the pod bay doors, Hal.
Ah, this is the best bit.
I'm sorry, Dave. I'm afraid I can't do that.
What's the problem?
I think you know what the problem is just as well as I do.
What are you talking about, Hal?
This mission is too important for me to allow you to jeopardize it.
I don't know what you're talking about, Hal.
I know that you and Frank were planning to disconnect me, and I'm afraid that's something I cannot allow to happen.
Where the hell did you get that idea, Hal?
Dave, although you took very thorough precautions in the pod against my hearing you, I could see your lips move.
He could see their lips move. Now, you may have heard in the news recently a DeepMind program, actually an Oxford program, was performing at a level of lip reading that was as good as any human. And the striking thing about that clip, whether you actually believe that we are close to or ever could be in a world of sentient computers, the achievements of our AIs are increasingly impressive. And in fact, the chess game that was played, of course, occurred in the 90s. A human champion defeated by a machine. But what does this actually tell us about the nature of AI? There's this wonderful phrase, I love it, artificial intelligence, the art of making computers that behave like the ones in movies, okay? And actually that's an awful lot of people's, it was my inspiration. You go out there and you see the sci-fi imagining and you think, well, let's get them built. Although, of course, they are generally mad, bad, and dangerous to know, as I've noted. Reality is, we're not close to general self-aware machines. What we have instead is a very interesting emerging space, and we have had for decades, as I'll want to demonstrate, of singular slivers of task-achieving computer programs that behave to a high level, but we don't have the faintest clue yet of what an integrated general intelligence looked like in all truth. We don't understand how to task transfer from one area of capability into another. And we'll look at that in a little bit more detail. The myth is in the films. The fact, as we know, is that AI is everywhere. And I think it's important we restate this because it's terribly, terribly easy to overlook the fact that the product of AI research, the last 40 years of AI laboratory research, is now embedded in every smartphone everyone is carrying around. It's embedded in the speech recognition systems, it's embedded in the recommender systems, the systems that hunt and look out for the information that you can speak using Siri into a perfectly acceptable speech recognition system. Truth is, it's not doing it anything like the way we thought we'd end up building speech recognition systems in the 70s and 80s, poured huge amounts of effort into that. And one of the parts of my talk tonight will be around this whole issue of the data deluge and what has really allowed many of our AI programs to succeed is unimagined quantities of training and learning data and the ability to apply methods which are very different than the ones that we thought would succeed at the time. AI is everywhere. It's in commercial robots that will clean your flat. Well, they do a passable job if you live in a nice rectilinear American flat. It doesn't work so well in a Cotswold cottage. And it's also tackling very hard problems where elements of AI assist in everything from surgery through to image interpretation and recognition. And this ubiquity of these slivers of task-achieving intelligence are everywhere and have been everywhere for a while and largely go unremarked, except on about a 10-year cycle, the world wakes up and gets very excited about where AI is and the fact that it might put us all out of our jobs or that it's an existential threat to the essential nature of humanity and so on. And so it was a couple of years, a year and a half ago with us here when we had essentially extraordinary interest when Stephen Hawking made the kind of claim that AI could be the greatest threat to humanity. Rampant AI, does it threaten humanity? And I spent quite a lot of time writing in the technical and popular press saying, no, it's not quite like that. What had actually unnerved, I think, Stephen Hawking had been the upgrade he received to his speech generation system. And it was a very smart upgrade indeed from a UK company which was doing an awful lot of predictive analytics to anticipate what it was that Stephen was likely to say, and through a very small amount of interface through this tiny kind of infrared reflector on a cheek muscle, and very efficient interrogation of thesauri of words and phrases that he uses. He has a much more powerful and effective speech generation system. So powerful that to him, it was as if the system was anticipating what he was going to say next. Okay. Now, we've all had that slightly spooky sense with some of our speech interactions with the machines, perhaps, often just irritating spookiness around it trying to correct your grammar when you know what you're trying to say and you'd rather it didn't get in the way. But this was a fact. And as I say, trying to get people to understand that if there's a threat around AI, I like to say, It's not the artificial intelligence that you've got to look out for, it's the natural stupidity. It's the fact that we're not very smart about thinking about where we might put the boundaries around machines that are going to increasingly run aspects of our critical infrastructure, run aspects of our daily lives. So I'll come back to the issue that one of the things that's driven this through is certainly the preponderance of data, a data deluge. The other thing that it is still, to those of us all in the business here, and many of you who will have been associated with AI for a long time, information technology and computer science for a long time, is of course our friend Moore's law, the observation that the computer power available to us is doubling at about every 15 months or so. And this little trace, I put this together recently just to remind myself, it's always good to go back to your own memory of devices. So here is the good old Motorola 6800, 1974, with 4,100 transistors. And boy, did we think that was smart at the time. This was a general purpose microprocessor that we could do many things for us. Shortly thereafter, it seemed, not so very long, just 5 years later, we'd had an extraordinary transition, a generation of Motorola chips to the 68,000, which was 68,000 transistors, more or less what it said on the tin. That was delivering huge opportunity to compute faster. The question I'd like to ask yourselves is, where has the wisdom and the insight in software engineering come that has kept anywhere near pace with this extraordinary contribution that our friends in electrical engineering have given us? Okay, because they've given us the Intel 8486 with over 1 million processors just 10 years later. Coppermine with 21 million in 2000. The Skylake processor that's actually driving my latest MacBook with almost 2 billion processors. And the modest phone we all carry around in our pockets, the Apple A8X with 3 billion transistors. That's a large reason why we're carrying lots of slivers of AI around in our pocket, because of the unreasonable amount of computing power that can run algorithms, many of which are hugely computationally intensive, whether they're employing methods, hidden Markov models, statistical methods, whether they're actually applying large constraint-based problem solvers to large amounts of incoming real-time data. That is the reality. And what's true for processing is no less true for storage. In fact, Kreider's law, the observation again that we have a log law, exponential growth in storage, really extraordinary. The IBM 3380 cabinet on the left there, this was 8 2.5 gigabyte disk systems. It cost $700,000. Cheap version that was, cheap version. And by 2005, we had a micro memory that could hold all of 128 megabytes. And just 10 years later, 128 gigabytes. That extraordinary reduction from 2,000 kilograms and 2.5 gigabytes to a thumb drive is something that, again, it's very easy. We kind of know it, but when you really materialize it and understand what that's given us, it's one of the principal reasons why the world has changed so extraordinarily around us. But I would say that, even back in the day, that great big giant cabinet and those not so fast processors, we were doing some pretty nifty stuff. This is work that I was doing in the 1990s. It was being published out in 2000. This is classic expert system technology. So knowledge-based systems, which were a fundamental approach in AI that said, if we could actually encapsulate or elicit the knowledge of a human operator and realize it as a set of rules that we could put in a simple rule execution engine, then we could provide decision support systems. And there was a lot of interest at the time, no less than now with drones, of these kind of technologies in military deployments. And this is for situational assessment, essentially trying to interpret radar tracks and the extent to which they may or may not have been threats. That real-time triaging of particular tracks. Around about the same time, actually earlier, 10 years earlier actually, we had been using a different style of knowledge representation, but still running what you might think of as a knowledge-based system that really for me illustrated why general AI was always going to prove to be very difficult. So this is a task, and we founded a company out of it, a project we had at Nottingham at the time, jointly with the chemical engineers. We wanted to build a system, and this was all the rage at the time, whether you were designing circuits or whether you were designing timetables. This was looking to take a logical diagram on the left, which is a process flow sheet for making particular chemical products, and lay it out in 3 dimensions. And actually, there's a huge amount of information in the diagram in the left, which can give you a large part of the solution on your right. Except it's not all in the diagram. There's a great deal of common sense engineering knowledge, which we had to elicit and codify. A nice example here is, in that diagram on the left, at certain crucial points in the chemical flow, and that is a logical specification. It's not a realization in 3D. Of course, that's the trick. There aren't pumps at a certain point of the process. There's no symbol for a pump. So the only way you could move stuff around this kind of plant was to exploit gravity flow. So you had to have a height difference between various kind of containers. Very standard trick in designing this stuff. Common sense chemical engineering knowledge that you had to anticipate if your system was ever going to perform. And the whole of this challenge, a good part of it was taking those common sense rules and internalizing them along with the kind of technical rules about how to interpret particular symbols as a particular plant and the rest of it. The fact you shouldn't place particular ignition sources close to very flammable for a good idea. The fact you should leave enough space between devices for access and safety and maintenance. All of that very mundane knowledge that an engineer just acquires in the course. Went well. I'm pleased to say the company was acquired by an American process control company called AspenTech, and it's still the basis of a lot of their products. These rule-based engines, built over decades, drive many of our routine processes now. And each time you become aware of a new enthusiasm for a new technique, remember there's a lot of legacy out there, and a lot of it is doing worthwhile and important tasks in the world. In the mid-90s, we had a moment when everybody woke up to the existential threat of AI because something significant happened. Kasparov was beaten by Deep Blue, won its first game on February the 10th in 1996, and finally beat the world's chess champion in a match, a 6-game match in May of 97. What happened in that series of games was that at a certain point, Kasparov literally became unnerved by the performance of the system, and he did something which humans do all the time. He endowed the system with more insight than it actually had. The behavior of the Deep Blue search algorithms, the way it could enumerate millions of potential search spaces and moves ahead and evaluate them, the way it had access to large database of different parts of the game, gave it real capability. But it wasn't reading Kasparov's mind. It wasn't anticipating, it didn't have a full-blown model of every aspect of how Kasparov was playing. It had a very optimized way of selecting moves itself. It gave the impression of real capability, and it had everybody talking about the emergence of a new kind of AI. When I left Edinburgh with my shiny PhD in the early 80s, there'd been a similar, about a decade earlier, there'd been a similar enthusiasm for AI. It was called, and it's partly inspired by a thing called the Japanese fifth generation intelligent computing initiative. It was going to build, the Japanese were the dominant in production and manufacturing industries, and the great fear was that they were going to end up building robots to automate all of this stuff. And so the Americans and Europeans and Brits all had to get in on that game. And we initiated a big research program here in the UK called the ALVI program, partly in response to that perceived economic and piece of national self-interest. You pick up a theme here. There's a certain point at which a particular capability is unleashed, particular set of methods are used, and people think this is the end of humankind. We're going to be put out of work. What's the future hold? At each point, I would say the machine capabilities got banked, became unremarkable. People moved on. You can buy extraordinary chess-playing software now that will run on your home PC. This rate of change continues. In about the late 90s, a number of us working in AI became very it was hard going. This rule-based approach, these particular programming approaches we had to trying to put symbol manipulation algorithms into computers and have them calculate effective responses. It was hard going. But that's pretty well how we did everything at the time. Natural language understanding was done by building grammars to parse sentence structures and analyze them and try and give them semantic sense. Everything was kind of dominated by a rule-based approach. And then people started to think that, well, if you looked into biology more seriously, you noticed that it wasn't obvious that the animal kingdom, successful adaptive systems, were running rule sets in quite this way. And you had to argue quite hard to believe that humans were doing it anything like that either. And this whole approach became known as Nouvelle AI, just the Nouvelle kind of cuisine. This was a new way of thinking about AI as opposed to the good old-fashioned AI. And it was a very interesting inversion of our assumptions. And one of the things that I think is very important for the current generation of AI students and graduates is to get a little history, because it's very easy not to read back into the early texts on knowledge representation and methods, because at each point at which new methods have been incorporated, really important insights were achieved, which will keep on turning up even in later generations of work. So in this approach to AI, you don't try and find explicit rules that say, if this a tank of this side is full of this chemical, don't place it any more than 5 meters away from this source here. Explicit rule-based reasoning. You looked at the world in terms of building complete systems. In this case, robotics was very impacted by this. Think about how biology solves the problem, and then you suddenly notice that actually oftentimes the problem isn't represented in the nervous system of the animal at all. And this very interesting phrase, the world is its own best model, that sometimes the problem been in AI that we spent so much time trying to take and build a model of the world inside the computer that we ended up doing far more computational work than we actually needed to. There's a couple of very nice examples I particularly liked in work that I was doing with a colleague called Barbara Webb, who specialized in the area of invertebrate robotics, building, and this is in the late 90s, so it's all the fashion now to build tiny little drones that will fly around, but then we were looking at very simple systems to understand what these biological principles were. On the left, there's a lovely example of a parasitic wasp laying its egg in another insect's eggs. And the remarkable thing about that wasp, it can insert just enough eggs such that the size of that egg will sustain all of those eggs to hatch. Okay, how does it work that out? Okay, clever piece of, if you like, determination or decision making. It turns out there's a very simple circuit simple set of nerves that connect the abdomen to the actual device that implants the eggs, and it measures the angle of separation. Okay, and so on a large egg with a bigger circumference, that's a much shallower angle. Okay, but it lays more eggs. Okay, so the way this piece of circuitry had evolved was beautifully optimized to the task it had. Wonderful example that's been quite extensively plagiarized and used in design is the so-called sky compass that honeybees and some insects have, which is rows of photoreceptors that are sensitive to polarized skylight. And effectively, natural skylight has an orientation, and what the bees do is orient themselves, and they have essentially a compass in their kind of nervous system that allows them to do a lot of the trace back to their hives and such when they're in search of foraging. Nice examples. And again, what that inspired a colleague and I to do was to look in a lot more detail at how biological systems were both built and how nervous systems could be constructed and evolved to suit them. So in this work that was reported in Transactions of the Royal Society, and another one in the Journal of Neuroscience, which is one of the leading neuroscience journals in the field, we were looking to take models of actual connectivity in neurons extremely seriously and see whether we couldn't engineer task-achieving behaviors by growing networks, neural networks. Now, neural networks have been around for some time, quite a long time, and their real first incarnation in the serious programming structures were in work from people like Romuald Hardin McClelland and Geoffrey Hinton in the early 90s, the so-called parallel distributed processing work. And here's the kind of thing we were doing. This is talking about 8086. There's a little Kepler robot here that's running a general processor and a little motor and a set of infrared detectors around the skirt there. And you could program this, these little robots. And the interesting thing about these robots is that they represent something that's very interesting about when you put real robots into the real world. Not all robots are identical. They're not all created equal. We aren't either. You know, I'm more or less myopic in one eye. We all kind of, we're not exactly entirely symmetric. One leg is usually longer than the other. Just the same with robots, you know. Turns out these little devices, the infrared sensors, have different levels of acuity. The engines run at very different, slightly different rates. They wear more on one tire than another. The whole world of nonlinearity, when you put a real robot in the real world, is thrown up. And what we were particularly interested in was, could we actually provide simple governing control systems, so simple neural networks which would control these robots. In this case, simple things like obstacle avoidance or phototropic, phototaxis, responses to go towards light or away from light, simple things like this. So in building obstacle avoidance systems, here's actually the inspiration we had was taken from an area of neuroscience which was discovering an awful lot about how two neurons connect up. And growth and connectivity between the synapses in neural systems is governed by the activity-dependent release of things called neurotrophic factors. They promote the growth and connection in real biological systems. And this is to give you a sense. These terms here, afferent and target neurons, so the things you're getting input into and what you're trying to project onto. NTF, a neurotrophic factor. What we're looking to do here is provide a simple mathematical model of how, well, it's relatively simple, partial differential equation, not too difficult. I'm not going to decode this too much, save to say that this is telling you how, through time, the release of neurotrophic factors is determined by the activity levels between axons that are connecting with each other. Okay. The trick in this time averaging, the summations in here, is all to try and be as faithful to the biology as possible. We can say more about that if any of you got real questions. It's very interesting because many neural networks have unrealistic assumptions about how these networks connect. So if I was just assuming that every robot was the same, and I wanted to build a neural network which would more or less connect the infrared detectors to the right and left motors through some hidden layers into neurons, then I wouldn't morally care that they were differently weighted, because actually each infrared ought to be more or less the same, and they ought to be all driving and contributing to the motor orientation signal. So what's the problem? Well, they're not. And we actually built our robotic system so they could learn through adjustments to their connection strengths to avoid collisions with the obstacles in their world. And these are actually two examples of actually evolved networks between different of our Kepra robots. And what they reflect is that these systems are able to adapt to the local body reality, the local constraints of each of those robots' actual real systems. Now that actually was a fascinating set of work we did. We actually extended it to slightly bigger robots here. It's very, if you know your robotics, you can exactly date when this work must have been done. This is a koala robot. We're trying to develop stereo vision systems here based on the same idea of neurotrophic factor release. And what we're trying to emulate is the development of what are called place cells, or optic retinal place cells in the optical processing system of mammals in this case. The interesting thing about this robot is it lives in this little world of office furniture. It develops receptive fields that show these vertical regularities, because actually it sees the world in a vertical axis very much more than any others. But what was very interesting about this work, it showed us how we could build networks which were genuinely inspired by biology. Now we'll come back to that, because that move from rule-based reasoning into neural networks via other methods such as constraint-based programming is very much a story of AI's progression and development into various types of programming framework. At the same time I was doing this, I was increasingly interested in the web. So this work going on. At the same time, I'd begun to become interested in a whole project that Tim Berners-Lee called the semantic web. And this is best thought of as scale of the web, massive numbers of websites and pages and content and data, and just no intelligence about the way those connections link, except where humans put hyperlinks into the web. The great genius of the web is that people take those web pages and they connect things up in relevant and meaningful ways to them. But if you were to open up your average web page, you'll remember that it's, and again, this dates exactly when we're doing this work. We began to do this work in the early 2000s. So here, and it still is the case largely, that many web pages that you will open up, if you open up the, and look into the code at the back, the HTML at the back, a page will describe what it's about. It will have some images, it will have different font types, it'll have some inline. You can see this is very old design values here, but there you go. But we always had a nice place for our web conference, you'll notice. Okay, this was Hawaii. What's the idea behind the semantic web? Well, basically to take some very old ideas in knowledge representation, really back to the early 70s, late 60s, and try and build a way of putting those representations into the web at scale. Well, what does that mean? Well, it means if I look as a human at this web page, I can tell you that that is a kind of object. It's an event, it's a conference, and that's its title. I can look at that part of the web page and see that that's the URL for the web page for the event. Or that in this case, down there is a photograph of an object. It's a photograph of a person. In fact, it's a photograph of a younger looking Tim Berners-Lee, who turns out to be a featured speaker at the conference. What if you were to open up the underlying representation of this page and insert into it at the various points in which these objects were being rendered semantic descriptions of what they were? Okay? And this is a very early version of what's called OWL, the ontology web language, which is essentially a vocabulary for describing the objects of interest in this area. So you could imagine developing a vocabulary or a semantics or an ontology, different uses of the word, for conferences. And such an ontology would have an expectation that at conferences there'll be speakers, there'll be events, there'll be a program, there'll be sets of venues where the lectures are being given. Very expectation driven, very old idea in AI, but what if you could take that simple representation and put it in every web page on the web? It's the essential idea behind the semantic web. And in the 2000s, that's where most of my AI interest lay. We had a number of very large projects looking at this, collaborations actually at the time with Sheffield. I was then at Southampton University, Edinburgh, the Open University, Aberdeen. We were using a range of methods to try and inject semantics into the web. Ultimately, that led to another spin-out company I was involved with called Garlic, which was trying to essentially build ways of looking for the leakage of your personal information onto the web. Essentially a form of identity theft and identity leakage software that was ultimately sold to Experian and still offered out as a service there. And I think the fascinating thing about that work is that a little discussed but clear fact is that Google use the semantic web all the time. Okay, they won't call it that. Their terminology is the knowledge graph. Okay, it's called the knowledge graph. The knowledge graph is the technology that allows them to take all of the copious information they're harvesting out of the web and linking it together, essentially in a graph-based representation with simple relational predicates that allow it to produce these things called knowledge panels, which are, again, stereotypical assemblies of information about objects of interest, when a person was born, where they were educated, and so on. There's huge amounts of Google energy going into extracting this information from many sources, including places like Wikipedia, Wikidata, and then curating it, often by hand, to make sure it's as good as it can be, and using that to inject more structure into the results that you get back when you do a Google search. So I've gone on, spent some time kind of talking through this to give you a sense that AI has gone through various eras, and at each point, a technology that belonged to an early era can manifest and get re-embedded in current contexts. I can't think of an area of AI that hasn't found essential deployment in our modern society, in the modern products we use. Everything from genetic algorithms to fuzzy logic that run many of the kind of routines in our wash spin cycles, in our washing machines. Many different methods developed at different eras, still and essentially in use. But the new kid on the block, as many of you may have heard, is an approach called deep learning or deep neural networks. I should say, though, that who's seen Watson? Who's seen the Watson IBM system here? Just put your hands up. It's like not so many. Okay, right, then you've seen this, but for the rest of you, this is not an IBM advert, I promise. Well, you're going to get a Google one in a minute. This is not a deep neural network. This is a very good example of how a whole set of AI techniques from different eras were assembled together to achieve something remarkable.
People are going to ask, how did it do that? How did it accomplish accomplish this task which before we thought only humans could ever hope to do.
David Hume held this view that sense and experience are the sole foundation of knowledge. Watson?
What is empiricism?
Watson is a question answering system. A question can be posed in natural language, and having read a whole bunch of information, data, documents, come up with a very precise answer to that question.
It's an information-seeking tool that's capable of understanding your question to make sure that you get what you want, and then delivers that content through a naturally flowing dialogue. Do you have one of those? I don't have one of those, right?
It's a human standing there with their carbon and water versus the computer with all of its silicon and its main memory and its disk.
After Germany invaded the Netherlands, this queen, her family, and cabinet fled to London. Maria?
Was Beatrix?
No. Watson?
Who is Wilhelmina?
That is correct.
Humans communicate very fluently in natural language, and that's where computers struggle dramatically, and that's where we want to make them better.
This U.S. president negotiated the Treaty of Portsmouth, ending the Russo-Japanese War. Watson?
Who is Theodore Roosevelt?
Good for $800.
The Jeopardy questions are tricky. They have puns in them, they have little jokes in them.
A famous red-coiffed clown, or just any incompetent fool. Watson?
Who is Bozo?
Nice! Good job, Watson.
I think we've gone from impressed to blown away.
This is really remarkable performance, and we know of no computer system that can come anywhere close to doing this question-answering task.
Well, good old IBM. Okay, so they're busy selling this as a solution now, not just to an arcane quiz game in America. Well, not so arcane, it's massively followed, and selling it as an approach to dealing with primary health consultations or general white-collar professional knowledge, such as making wills. How does it do it? It does it by incorporating voluminous amounts of web-based knowledge, semantic web representations, bunch of machine learning techniques to actually understand and parse natural language, but generally rather traditional methods. I mean, the ones I've been talking about so far. And it's really quite dramatic how capable Watson is, but it has to be so extraordinarily carefully trained on each task to which it's deployed. They had the benefit in playing that quiz game there of every recorded game of Jeopardy there'd ever been. A massive database of training examples. They had a strong sense of what the structure of questions were and how you could actually use general knowledge to solve those problems. But if you're going to build a general physician Watson engine, you've got to internalize primary medicine. You've got to understand the kinds of questions that the first encounters between you and your physician would involve. Massive amounts of customization. This just doesn't happen without very large amounts of knowledge engineering effort. But nevertheless, a real high watermark, you would argue, for AI, and recently too, in just the last few years. But then we got the new kid on the block from another big IT company, from Google, deep neural networks. How many people have seen the arcade game from neural networks? Hands up. Oh, not many. This is good. This is good. Okay, I'm going to switch off the very irritating soundtrack on this. It will sound you mad and show you just this behavior. Yeah, okay. So this is a form of recurrent neural network. So essentially a system which can organize through arbitrary levels of network structure. So you have a set of input nodes that represent a problem, and you're effectively trying to get a set of outputs. In this case, the task you're trying to solve is control those paddles you used to have on those simple arcade games. There it is, breakout. Yeah, trying to kind of control that ball to break out. Now this is DeepMind just starting out. Pretty hopeless. Okay. within a representation of this problem as a very large matrix of pixels, there are correlations between the paddles and the trajectory of those balls and whether you're going to increment the score at all and get better. This is after a certain amount of training, not huge amounts, but about 2 hours worth of training. And you can see it's got pretty good control. It's not been supervised to do this. It's learned the association between paddle, incoming and outgoing. After about 4 hours, something really spooky happens. The system starts to play at superhuman levels of behavior, and it works out the great tactic that all breakout players know, that the smart thing to do is to get the ball behind the wall. Now, I used loads of anthropomorphic terms like it worked out that, it did this. In fact, the question we ask ourselves when we look at these deep recurrent networks is what is actually being learnt. And the actual architecture of these networks is arbitrary, well, not arbitrary, but many levels of stacked neuron layer. And each layer is trying to work out an aspect of generalization of part of the problem space. Not represented as rules, very similar to the neural networks I showed you controlling the robots. This is about weight adjustment. It's about adjusting the connectivity weights based on a set of local parameter calculations about how the actual weights around it are being adjusted as it represents a problem. Typically, it works very well where problems can be redescribed in terms of large matrices inputs. Turns out there are quite a few problems like that. This is one intriguing aspect of this work is that you start to imagine that as you look at the weight matrix across all those layers, do you get anything like neural maps? Bits of the connection matrix that represent particular phases of the game or aspects of control of the game. And the culmination of this was, of course, the very recent achievement of AlphaGo, DeepMind's system that managed to beat the world's best Go player. Now, the reason this really shook a lot of AI theorists as well is that we thought this was some way off. We didn't imagine we'd have the world's best Go player defeated by this style of program because, well, the search space was so large. And one of the reasons that we could imagine, even chess was bad enough, but we could throw enough power at it ultimately that we could actually look quite far ahead in the game tree. But in Go, it's a huge space of possible future positions. But actually, the genius of AlphaGo is that, first of all, they kind of train the system up in a supervised learning model where essentially they have thousands and thousands of online games where they can actually get the system to begin to perform to an adequate level, and then it's actually allowed to play itself and continue to improve. And again, it's not entirely just about the neural network. There are components in the architecture, so-called policy engine, which actually evaluate whether or not the overall behavior of the system looks sensible or rational. So it's, again, this idea of a mixed architecture. Now, I think the reason people have gotten very excited about this particular stage of development in AI is that we have here a style of program construction which have these deep levels of forward processing, networks on top of networks on top of networks, pushing signals through the system. And actually, aspects of neural processing look a lot like this. So if I'm going to recognize an object in the world, if you look at what happens in real neurology, various parts of the brain are involved, from the retina back into V1 in the back of the brain here, the actual visual cortex, and then back through parts of the brain where essentially more and more semantic processing is going on to eventually identify the thing you're looking at, for example, as a picture of a cat. The question is, do these sorts of architectures begin to give us a sense of engaging with real neurology? And I have to say that I think the the work that's ongoing here is impressive. There's no question about that. This is a wonderful piece of work, again, that appeared, favorite journal of mine, the Journal of Neuroscience, just a couple of years ago, where they're showing how these recurrent neural networks, these deep neural networks, can begin to abstract out aspects of complex picture identification through to much more familiar stages of symbolic representation that we might be finding equivalents of in actual human visual processing, to the extent that they're now able to imagine how those networks might correspond to real brain topology. Early days, and a final thing I'll leave you with here is something that is really quite spooky. This is where neural nets are kind of wanting to go. This is kind of only the work that you can do when you're dealing with real medical patients who have a severe problem. This is they're actually recording here a patient who's undergoing some necessary surgery, volunteered to do this, and they're actually taking brain recordings of the stimulation of the auditory cortex. So this person is not only just having a piece of brain surgery, he's cooperating in a piece of neuroscience where he's being shown pictures of words and being asked to vocalize them. Okay. And what they're now doing is kind of going one step further, which is to say, if we look at the complex neural signals, the brain signals from that exposure to a stimulus, well, can we build neural networks to recognize those kinds of signals arrays and predictively anticipate what that signal represents? And let me just show you an example of that. I have to just crash out of
Structure. Town. Doubt. Property.
It's not perfect, is it?
Pencil. Waldo. Waldo.
A kind of ghostly representations of what that word would have sounded like. And the interesting thing about this work is that now beginning to do it with kind of visual presentations as well, visual stimuli. So you can, perhaps that's what next week's talk's going to be, or the next talk, The Ghost in the Machine, may be exactly about this, I don't know. But it is a fascinating thought that we are now beginning with our AI systems. And the ambition of what we're trying to do here, to see this kind of this convergence to problems that really did feel an awfully long way away. So had I another hour, I'd take you on a further journey into the extent to which I think there's another really interesting twist on this, and I'll just give you a taster for it, and then take questions. One of the titles, one of the phrases in my title tonight's talk was social machines, and I think the thing that we have been failing to recognize is that with all of the talk of autonomous AI and the developments in that area, there is another kind of AI. It's called augmented intelligence, and it's the recognition that when you put these very powerful computational systems, large data sets, and actual human processes together, you get a very interesting kind of blended system. It's a system that we call social machines. It's an area of research that I'm currently involved with my colleague Tim Berners-Lee and others, some of my researchers here tonight, working on the same project. And here we're trying to understand what's the requirements, design and engineering when we're seeking to build systems at scale that have thousands of human components, machine components, and data. It gives us a new kind of opportunity, because I've talked a lot about the machine exponents, Kreider's law, Moore's law. There's this exponent, right? There's a lot of us on the planet, all running pretty decent neural processors most of the time. And together we can achieve these remarkable outcomes. And just to give you a sense of that, let me just show you perhaps a couple of examples. This is what happens when you're asked to kind of do that pesky task where you have to sort of recognize a difficult to read word, you know, when you're trying to log on to a site or do something like that. These are called captures. What you were doing once upon a time, well, you still are, when you recognize those kinds of images, which are words that are difficult for optical character recognition systems to actually recognize, is that Google is harvesting a tiny bit of your natural mental processing to solve a problem at scale that it can't solve. At one point, it was processing 20 million words a day because it had also the audacious proposal to actually digitize the world's out-of-copyright literature. Okay? And much of that was faded, poor type, and it couldn't recognize reliably. So it would put all those hard-to-recognize words out to you, me, and everybody else on the planet to recognize for it. Okay? That's a wonderful example of what's called human computation. Now imagine that at scale, where your cognitive skills are being matched to the machine skills to solve a problem at scale. Well, it's happening all the time. We don't really recognize it for that. Here's another great example. This is called iWire. This is this is a great example. They're trying to map, and it's kind of a nice tie back to the visual processing stuff I talked about earlier, the visual cortex. They're trying to take real maps of the visual cortex and map every piece of wiring in individuals. Okay, so detailed brain scans of individuals. Of course, we're all different, so it's a hell of a job. But they use automated software to try and trace it, but the automated software isn't perfect. It makes mistakes. So what this online game has you do is to become the ninja to repair those networks. Okay? Humans can see where the actual traces and connections go in a way that machines can't. Here at Oxford, there's been the wonderful Galaxy Zoo project that Chris Lintott runs, where there are so many astronomy images coming down from our telescopes in the sky, and the astronomers are too poor to afford really advanced programs for software development. The genius idea was get the Mark I eyeball and brain trained to recognize different kinds of images, and we're extraordinarily good at it very quickly. So in this particular task, your job was to identify different types of galaxy. We do it supremely well to the extent that people discover new objects unknown to astronomy, and all sorts of good things happen. To the extent that we can now run machine learning algorithms over the results of all those processes of machine images and classify you as different kinds of cognitive processor that can do differently difficult jobs in recognizing astronomical images. I can put you in a bucket and say, you're good for that bit of the task. You're good for that bit of the task. So what we're looking to do is componentize the human and machine elements and put them together in new forms of augmented intelligence. And lest that sound too spooky, let me give you a sense that this is also high-minded. Because if we can do that effectively, if we can bring people together at scale, with data, with machine algorithms, we can achieve remarkable things. This is my favorite current example. This is what happened when the earthquake hit Kathmandu. In 48 hours, we managed to assemble 4,000 mappers with software and tools to map the ruined roadways and trafficways and estimate the damage in Kathmandu. That assembly of human talent, machine talent, data, and our AIs promises, I think, not a threat to humanity, but a new kind of opportunity. Thank you. That was an hour, I'm sorry, I talked rather a lot. No.
It's time for questions.
Yes, sorry, yes.
Nigel, thanks very much for making what may be a very complex subject understandable. I've got a one question I had, but it goes back about 10 slides, where you're describing automated intelligent social machines, and you said it's governed by social processes, individual action and coordinated, mediated by, what was it?
It would be the shared communication substrate of the web. Yeah.
Okay.
So the idea there is that this is Tim's definition, actually. No, I think this might be ours, actually. This is a modification of it. The thought here is that these assemblies are really only brought into being by the, if you like, connective substrate that is the web. I mean, actually, people have done this in the past. You know, small groups of people working in Hut 8 at Bletchley Park were kind of solving problems with machine assistance, but they were at a scale that was necessarily limited. Here, we're talking about being able to recruit 4,000 people in 48 hours via the agency of the web, or people who are distributed across geography via the agency of the web.
Can I stop you there? Because that was not so much a question as a point of information.
Yeah.
But now can I ask you my question, please? And that is that I'm sort of looking at the practical realities of HR. Sorry, not HR, AI. And I've just sort of off the top of my head putting down 4 possibilities that may eventuate through AI. And I'd like you, interestingly, to either refute or confirm those possibilities. And the first one is to...
Can I plead the Fifth Amendment?
All right.
Go on.
Number 1, the possibility of curing or compensating for strokes. Number 2, being able to read lips far away with a telescope inbuilt into your smartphone and knowing what people are saying. Number 4, I think, is for AI to handle your email by you simply inputting macros verbally.
All right, okay. Well, number 1 and 2, yes, they're going to happen. I mean, it may sound preposterous, but actually, we're well on we've got pretty good lip reading software now. It's undergone a real phase shift in its capability. Yeah, smart. I mean, it's a bit scary, actually, if you think about it. So the HAL model, the scary bit about HAL was that he managed to read the lips and kind of decode the conversation. Lots of people would be interested in that capability, I'm sure. Stroke assistance, I think we're already seeing that with kind of intelligent prosthetics, which seek to compensate. And actually, of course, the fascinating thing about stroke rehabilitation is that when you look at it in detail, the ability of the brain, the plasticity of the actual brain to recompensate itself is an extraordinary thing. I mean, again, this kind of very strange idea that somehow we stop being able to do that past about 15 or 16. It's not at all the case. Whether we'll be able to do that with more accuracy and more effectiveness as we think about how we can align machine processing with, for example, brain states, I'm sure that's going to happen. I mean, because effectively we can see the genesis of that with those very simple alignments of EEGs effectively with particular output states. So you want to say duck, water, but you've got some dysphasia. You can't actually produce the sound, but the intention is there. The question is, how much of the intention can you capture off the brain signal and then actually verbalize on behalf of the patient? And I think that's very early steps to do some of that with locked-in patients that one was reading about recently. I mean, that very, very simple sorts of interrogation there, but potentially work in that space.
And what about the day-to-day issue of handling our mountains?
Oh, email. I think that's, you know what? Just unplug. I mean, I think that's what I... Yeah, that may be beyond even AI, I suspect.
Yeah, I was just picking up on that. There is an example where, with iPhones, blind people can see.
Yeah.
There's a service that I read about where you can actually just connect to somebody else.
The thing that has really been transformational, I think we did, and because of the emergent properties of these slivers of capability, And do not confuse that with the machine sitting there feeling pleased with itself and sentient and self-aware. But these emergent capabilities mean there'll be some remarkable augmentations, and that I do wonder how it will not be very long before we have the Douglas Adams Babelfish. It will just be an online service that's cloud mediated, and kind of interesting what that might do to the dominance of the English language, because you won't have to learn necessarily the other language. Yeah. So one thing we've learnt about the web is how strong locality principles are. All this connectivity at global scale, that it's amazing how much it puts you into contact with your local context as well. Anyway. Yes?
So there's a lot of fields where there's some sort of responsibility of humans to make a verifiable choice, like engineers putting their stamps on a document, doctors making a diagnosis. What do you think the sort of legal roadmap for putting AI into these kinds of fields where humans have some sort of moral responsibility?
Well, the question of I'm kind of repeating the question because it's the way they're taking the audio. I realised I hadn't done that on the previous one, so you'll have to kind of splice that in. Should we? Well, the whole point about an ethical framework for the deployment and use of AIs, it's certainly accentuated in the case of AIs, or it seems to be, but it's a general problem in software. So verifiability, certification, what standards do we expect the system to run to, and are we entirely happy that simply because the system can, that's sufficient warrant about whether it was behaving reasonably? I mean, so this is a whole field that's receiving a lot of attention and some funding actually, called algorithmic accountability, as I'm sure you're aware. I think that's a very pressing issue. I think the challenges there are as much to do with the social institutions that we will need to engineer to kind of deal with this and recognize it. And we're not always very good at, we're sometimes good at it and sometimes just miss it. So my example that I think represents the best of this was the Human Embryology and Fertilization Authority, which was set up in the UK in advance of much of the technology and science having been done, but they could see the ethics, the challenge of this whole area. So they put some regulatory authority in place before it all burst onto the scene. And I think where science can be anticipatory and society can think about the problem in advance of just being in a moral panic, that really helps. So, and there's clearly some areas where just the regulatory requirements, whether that's where you would think so. So, I mean, the amount of thinking that's going into autonomous vehicles at the moment is quite a good example of that, whether it's going to play out in a way that that is going to support innovation. The danger people have is that, how you get this balance between damping innovation and just being prudent and understanding the limits of the systems. One of the great challenges still in all of our AI is the thing that human cognition, the best types of human cognition have, which is self-awareness and awareness of limitations. So it's the meta-knowledge that you have about what you don't know. And that is actually not often a hallmark of most of our AI systems. We put them in situations and they do what they do, and then we're surprised when they find themselves in some kind of context they hadn't encountered before and behave in ways that we don't like. Yeah.
Is there anything that you feel that there is concern for the future?
Oh, there's plenty of concern for the future. I mean, I'm trying to be somewhat upbeat here. I mean, there's lots of reasons why you might fear. There's a genuine question about whether we need serious arms limitation statutes for AI. I mean, we're starting to see people wake up to the fact that unlimited cyber warfare probably isn't the most efficient way for modern nation states to deal with one another, and until we work out how, in a certain sense, we set up international institutions to manage that, it'll be everywhere. But if you think back to what we had to do for nuclear and biological and chemical warfare, these were technologies that were dual use, and at some point we had to get to a position where we didn't just let things take care of themselves. So I think weaponization of AI is a serious challenge, and we need to be alert to it. So I would like us to be thinking about it rather than hoping it'll take care of itself. Yes.
So thank you for sharing about the the courses I'm doing at uni. So I also want to talk about the future, especially about social machines. So social machines are a collaboration of humans and machines, and you showed some very great examples like reCAPTCHA and Gexisoo, both of which I've used. Gexisoo voluntarily and reCAPTCHA involuntarily.
Yeah, involuntary, that's right.
But it's quite interesting to note that the systems you show are mostly people volunteering time.
Yeah.
And it seems like right now there's a trend to rely more on machines than humans. Simply, I think, because of the fact that machines are quite cheap to throw at. Like, you can just pull up many servers at one go, while if you want to get a critical mass of humans, you kind of need some time to gather this mass, especially if people are volunteering this time.
Yeah.
So how do you think the future of social machines is going to work when, like, machine time seems to be less valuable than human time?
Yeah, I think you're right. There is a bit of an arms race going on here, but I think there are plenty of tasks where the human is still, in a sense, able to make finer discriminations than our current machine technology. It's not to say it won't ultimately, and there'll be always a. So in other contexts like Fold-it, you've probably done Fold-it. The three-dimensional protein folding games, where there's an awful lot of domain knowledge to be acquired to work out the constraints. So this is still a very, very big search space as far as even standing up large amounts of computational services. So I think there are a few areas, and then the areas like the mapping that we saw those volunteers doing in Nepal was actually quite imprecisely framed. So they were doing lots of things through having been trained and inducted, but also able to ask questions of one another quickly, and experts there to kind of fill the gaps in the specification. So not everything is as well specified as classify this image or find out what this word is. And where there are issues like, what's this pattern telling us, humans are still extraordinarily powerful as assessors and context-aware machines. So I see plenty of mileage in this, actually. Yeah. Edmund.
You talked about biologically inspired neural networks. I was wondering how far you think this might go in terms of sort of scale.
I mean, that's probably the most optimistic talk I've given on actual neural networks in a while, because for a long time, having worked in them as well, I was very skeptical of their abstractions are very coarse. And we keep breaking out in a certain sense to another layer of complexity, and they reveal something that surprises us in terms of their capacity. But in truth, if you look at real neural networks, I mean, what isn't in your modern deep neural network? Well, lateral connectivity. There's no connectivity between. There is some reentrance, but there's no modularization in the way that we see in actual neural architectures. Although again, people looking at that, the detail, each node is an extraordinarily simple processor for all of its the operations that are applied to it, compared to a real synapse. The dendritic, the very fine structure of a synapse is already an extraordinarily complex affair, and we're barely aware of how that's being operated. We're not entirely sure what other substrates in brain chemistry are doing either. So, but I think it's still rich. And of course, when we go to simple animal models, the Drosophila or C. elegans, those are really being pretty thoroughly digitized or virtualized now, and still yielding insights, but that work's well underway. So I think, and then the other side of that is the attempts to culture real neurons and connect them to surrounding circuitry. So that's the other approach in this, which is to actually have real wetware connected into other parts of electronic substrate.
But if you have a very simple organism, like I guess a snail or something,
yeah,
and you build a complete electronic
yeah.
version of it, and you
yeah.
switch it on,
yeah.
how would you know what it was doing?
Well, it would be doing what snails do, if you've got a good model. I mean, I think that's the thing. What you discover in the biologically inspired work is that the natural tendency to want to give a rational engineer's description of what the system is doing works only up to a point, because the embodiment of what the system's doing doesn't naturally carve down into it's doing task X now or task Y. It's getting all.
But wouldn't it be great to actually understand how the different parts of the brain, cell architecture, what they actually do.
Sure, sure, and I mean, and that's always been the kind of holy grail here in all this work. But it's and with all the wondrous developments in imaging and our insights, it's still. I've been surprised though at how far this new generation of neural models has got us to rethink things like the fundamental nature of representation. So what we've learned in a lot of our AI is that how we naturally think about how the world might be represented in our heads is no kind of approximation to what's going on. So your face is represented in my neural cortex as a set of spatial harmonics. What? You know, not your fine nose or your proud jaw. It's not like that. So yeah. That insight's still to be had.
Can we train artificial neural networks to execute tasks in weight differentiation sequence?
You mean temporally?
To devise a algorithm to execute tasks in a sequence.
Yeah, yeah. So to capture temporal regularity.
Temporal regularity.
Yeah.
Is weight differentiation.
Yes. Yes, to some extent you can. I mean, I think the issue is that it's an interesting point you make. An awful lot of the examples we see are, in some sense, episodic, and they're not necessarily looking at extended amounts of recurrent structure. Well, they are. Quite a few of them are now, increasingly. I mean, work on acoustic recognition. So they're looking to take a timeline and understand what the actual weight variations through time are telling you about temporal structure. Yeah. The question on the other side is, are we exploiting what we think brains do when they encode representations in temporal representations in the brain? So it's kind of a two-way dialogue there.
Yeah, I was thinking along that line, but the sequence, executing, instead of a single task, like get a sequence of tasks.
Yeah.
Executing them at the same time. This will actually increase the processing speed.
I mean, if you think about and if you think about the video game that was shown there, what effectively that has done is take an extraordinary. It has found, if you like, the extended temporal correlations in the data and built weights to kind of deal with that patterning. So yeah, it's there. Ulrich.
So you start out by mentioning these words about super intelligences at a general level that might take over the world and so on, and suggesting that wasn't really something to worry about.
Yep.
But I mean, there's lots of people thinking about the challenges there at the Future of Humanity Institute.
Yeah.
If you speak, there's lots of people at Deep Minds that when you speak with them, they'll sort of using lots of concepts from Nick Bostrom's book on the topic, and we'll be talking about, what the challenges are if we get like a quick takeoff and so on. Dempsey Savage is also worrying about it himself.
Yeah.
So what I want to ask is, do you think that it's just something that just isn't a high priority for us to worry about for now?
No. I think there are lots of ways. There are lots of ways to be. We have to be careful on a number of fronts. I think to characterize hard takeoff or the singularity as the thing we need to worry about is just to not to recognize where the real imminent dangers are. Of course, if you had some kind of very dull, self-reproducing consumer of your kind of natural resources, a la Bostrom's kind of paperclip manufacturer, that would be, which idiot would allow that system into the world? It's like very, very badly engineered, genetically modified crops. There could be. You could imagine somebody working really hard to build something stupidly resilient and of no interest other than just kind of consuming the air we breathe, and that would be clearly daft. There have been lots of daft ways in which our technology has tended to be misappropriated over time. I think you've got to differentiate that from this idea that we will just reach a point at which the networks will become so super smart because what? I mean, will we suddenly have a network that can aggregate and train over the sum of all networks as the learning experience? Would that be it? What the nature of general task transfer and general sort of self-aware systems is, that is still the hard question. And I see nothing in the work to date, tantalizing though it is about the nature of deep representations, impressive though it is at the level of achieving specific task outcomes, that give me to believe that's the worry. The worry is putting all that capability onto a drone with rules of engagement that don't require it to kind of have oversight by a human controller. Yeah.
I'm unfortunately old enough to remember back in the sort of 1980s or so, when expert systems were the sort of holy grail.
So am I.
and one of the aspects I seem to remember there was that you could ask them how it had arrived at the conclusion it's arrived at. I get the impression now, particularly with just taking lots of data and doing machine learning and that, that we can't actually ask that question.
I think it doesn't naturally come with the architecture. So that's a really interesting point. There are people worrying about that a lot. So there's a whole area, transparent machine learning initiative, which is trying to work out how you can actually engineer things so that there is a recapitulation of that amounts to a kind of explanation. So almost putting a symbolic interpretation onto all of those stages in the weight formation. But with a rule-based system, you know, the what and how were very natural parts of the architecture. You got very tedious kinds of explanations typically, but the whole thing had been programmed in terms of these conditionals, so you could see it. And actually a lot of AI, each AI technology has come with a different style of explanation-based justification, if you think about it. So theorem provers would do it one way, genetic algorithm would do it another. Neural networks have this challenge. Explanation-based machine learning was actually fundamentally premised on the fact that you learn by giving it examples, positive examples, that it could analyze and understand why there were positive examples of the concept being learned. So you had the decomposition of the problem built into the style of the algorithm. So there is that challenge, and I think these very data-rich approaches, they do have that challenge, I think, which is how do you make the decisions accountable that you have. Yeah.
Well, thank you very much for a very stimulating and interesting talk. And enjoyable one too.
So, thank you. Thank you very much.